2-9.2, the radar problem. Did you all look at that thing or not? How many? I'm just curious because I want to do this one because you're going to see something like this again. I mean, think about this. My background is radar. That's what I use this stuff for. Probably I'm going to ask them, can you read 2-9.2, the problem? I want to do this just for completeness, then I'll get on with my lecture. By the way, how many have classes this week besides on Monday? Anybody? All of you are off? Are you going home? If you are driving, I warn you about one thing, the police. They have, and there's a limited number of violators out there, and there are certain things that police have to do, and there's activities, so just think about it, just drive carefully, I'm warning you about this. All right, 2-9.2.
In a radar system, the reflected signal pulses may have amplitudes that are Rayleigh distributed.
Hold on for 1 second. So now I'm just going to call the signal of the echo return, and it would be a voltage, but I'm going to use R because, frankly, Rayleigh distribution, R makes sense. And this means the actual probability dense, or this would be the cumulative distribution function, would be 1 minus EXP to the minus R squared over 2 sigma squared. Now that sigma technically is going to be the sigma of X and Y variables. Remember what I've always been stressing, that is not the Rayleigh standard or the Rayleigh variance, sigma squared. Okay, go ahead.
Let the mean value of the pulses be pi over 2 squared, or square root of 2.
All right, that's a nice value for a reason. Let me put it up here before you finish. So for a Rayleigh distribution, the mean value is equal to the square root of pi over 2 times sigma. Y'all with me on this, class? How many remember that? I'm just curious. And that would be sigma x or sigma y. And then the mean squared value is what? 2 sigma squared. Do you remember that? If you don't, for the Rayleigh distribution, I probably would give that information to you just because it's not that, you don't use it that much. Now the Gaussian stuff, for any information about the Gaussian probabilities, I expect you to know how to do that with your calculators. And I want to be clear about that. Everybody with me on this? Make sure that that's clear in your mind. Anyway, go ahead.
However, the only pulses that are displayed on the radar scope are those for which the pulse amplitude R is greater than some threshold or not, in order that the effects of system noise can be suppressed.
Yeah, go ahead.
First part A, determine the probability density function of the display of pulses. That is, find f of R given that R is greater.
Yeah, and this is a great problem in a way you have to apply conditional probability theory. And you're going to see a little bit later in chapter 3, there'll be a way to simplify this. So first I have to put the Rayleigh probability density function down. And I'm going to use capital R here. And that's R right here, if you look at it, over sigma squared. And that would be like sigma x or sigma y, exp to the minus R squared over 2 sigma squared. And this is for R, of course, greater than 0, less than infinity. Greater than or equal to, it doesn't matter for this, it's continuous. Now, we want the conditional probability density, right? And if you think about the way it was done before, you basically had like, the way it was f of R given some event M occurred. Do you recall this? That was the symbols we used. How many of you remember that? Remember we used that slash n. And what that is going to be equal to is going to be this, f of R of R. This is the original density function. But then down here, it's going to be the probability that the event occurred they're talking about. Y'all follow me? The reason you do that, it normalizes. If you think about just f of R here, if you integrate that from 0 to infinity, you get 1, right? Now, if an event occurred, say R greater than some of that, now now the density function based on that is only gonna be from R0 to infinity, and the area under that has to be one. Y'all follow me? How many do you follow me on this, or anytime I see a head, I think I'm doing something wrong, but I'm trying to read the class. So if you don't, now's the time to let me know and I'll try to explain it better. So down here, what we need is the probability that R is greater than N, or greater than R naught. Y'all follow me on this one? So what would that be? Well, this right here is the probability that R is less than or equal to that value, correct? So the probability it's greater than that value would be 1 minus this, right? But I'll use smaller or not. So that means down here, you're gonna get FR just, or I shouldn't say FR. It should be EXP, and here it would be minus R naught over 2 sigma squared. And now, how many understand what I've done here? Are you good on that one? Do you understand? I want to make sure. Do you understand? I've got to make sure that at least I'm getting this point across. So if that's the case, now you can do this a lot of ways. You can take that and integrate it up here if you want. And let me just show you what I mean. I can take R right here over sigma naught or sigma x squared, and then I can take EXP. It would be minus R squared, but then if this comes upstairs, it would be, I'll write it down one time. And then it would be EXP to the plus R naught squared over 2 sigma squared. I'm just showing you, if you bring that from denominator to numerator, this would be the actual statement. Mathematical statement. So then you could write it as simply R, depending on how you want to do this, over sigma x squared, and then you could write it EXP to the minus quantity R squared minus R naught squared. You don't have to do it this way, by the way. 2 sigma squared, and this is valid for R greater than R naught less than infinity. Now, well, when you write it down, just take a look. This is problem 2-9.2. But this is a density function. That's acceptable, this is acceptable, this is acceptable. It doesn't matter how you write it, as long as you understand it. You with me? So then what do they ask for?
Find the conditional mean of the displaced pulses if R naught equals 0.5.
Okay, great problem. I'm saying this for a reason. I'm going to come back over here, and you see how this is important. You notice these things. When you look over here, the mean value was square root of pi over 2 times sigma x, right? But here's the defining mean value for our problem. What does that tell you? Sigma x equals 1. Does everybody see that? Here it is in general for any distribution, right? That's the mean value, correct, class? Of the Rayleigh distribution. For R, specifically, it's this. So you can see I have pi over 2, exactly. The only thing it can be is 1. Does everybody see that? So we get the mean value, or I'm sorry, the standard deviation right there from just examining that. There's nothing else required. Now, after that's done, they want the mean value of this distribution, right? So now we go ahead and say the expected value of, you might say, R given M is going to be really equal to the integral from R naught to infinity of the conditional probability. I'm going to do it this way. I'm simply going to take this and I'm going to extract this value because he gives the value of R naught as 1/2. Correct, class? So if R naught is equal to 1/2 for this part, now I'm going to go ahead and say I'll take this, and this is 1/2 squared over 2, because sigma is 1. Sigma squared, therefore, is 1. And then I have to do this integral from really plus r naught, or plus 1/2, I'll just put 1/2, to infinity, right, of simply r exp to the minus r squared over 2 dr. And doing that integral, now your calculators will do it, but there's a trick on this one. When you look at this right here, remember, I shouldn't say a trick, it's obvious. Remember, if you integrate the value from 0 to r of r over sigma squared exp to the minus r squared over 2 sigma squared, right here, dr, you get 1 minus exp to the minus r squared over 2 sigma squared. Do y'all remember? We could do this by an antiderivative. We could say if actually du is equal to this, then u, if you take a look at this, would be equal to, okay, you might as well do this. If you let u equal to, and I'll do it this way, r over sigma squared exp, actually that's du, sorry. If you let u equal to exp to the minus r squared over 2 sigma squared, therefore du would be equal to minus 2r over 2 sigma squared exp the minus r squared over 2 sigma squared. And if you look at this, this right here is exactly what we have inside the integrator. So the du is right here, only it's going to be a minus. If you integrate this, you get this, and by changing the actual minus sign, you get this. Just, you follow the logic on this one? Okay, back to this thing. Now if it goes from 1/2 to infinity, now what you're going to get is this. This is going to still have to take that exp and, hold on for a second. That actually should be plus right here, my bad. This is a plus. So it's going to be exp, so 1/2 squared is 1/4, so this is 1/8 here. 1/8, pardon me. And then, if you integrate this, you're going to get exp to the minus r squared over 2 sigma squared, and you have to evaluate it at those limits. You all with me on this, class? Yes, sir.
Why would we not use r squared times exp? Because when we're finding the mean value, don't we multiply that?
No, when you get mean value, you're going to take we want the mean of r, right? It's r times the density function. It's r squared. My bad. Hold on. Yeah, this should be an r squared. That is my on mean. This should be an r squared right here. And let's see here. I believe that's right. Correct, class? I'm sorry about that. It wasn't intentional, trust me. So if I do this, by the way, what does he have in the book when he does this one? He does the solution. He does this integration, I believe. This is going to be an integration by parts.
He writes it as, I guess, he has and he uses gamma squared, but it'd be gamma squared minus
Gamma?
point.
Oh, all right. He's doing, that's effectively, instead of r, he's using gamma.
Okay.
All right, so he has r squared basically. Maybe that is r squared. R squared e to the minus 1/2 r squared minus that. And then he uses a a VDU integration, but at the end of the day, what do you get for that? I wouldn't ask you to do this integral unless I told you specifically ahead of time you're gonna need to do it, but you're absolutely right about that. What is that?
He gets 1.376.
I actually did this on MathCAD. I didn't do it last night, it was, I think, Thursday night, but it is the right answer in there. And what's the third part of that problem?
It's just 2 words.
That's it?
That's it.
Okay, I'm gonna tell you, for this one specifically, that integration, if I was gonna expect you to do it on a test, I would tell you ahead of time, know how to do that integration. I'm not gonna ask you to do crazy integrals, unless I give you a little warning you're gonna see. Okay, that's that problem. Now I wanna get to this, in chapter 3 of that book, and I don't know the actual pages in Stanley Chan's book, but what we're gonna talk about, density functions of 2 variables or more. And this is common. But these appear a lot of times, well, in radar problems they appear, but you can have density functions that are a function of x and y as far as the actual elevation and azimuth, or the actual vertical distance and horizontal distance. These kind of things happen all the time. But density functions of 2 or more dimensions that you would run into in the real world, for instance, for microelectronic processing. Now, everybody I think has been exposed to what VLSI is, very large scale integrated circuits. What you have to do on them a lot of times is you have to put, basically what you want to do is delineate a pattern. That means somehow you have lines, you want conducting, then you have transistors you have to create, and you have to develop oxide layers and everything like this, where you get tens of thousands of transistors on a small little piece of silicon on a surface. When they're doing any of this work, there's always a statistical variation, a line width statistical variation in just about everything that they know, because the process is done many, many times, and they collect information and they can develop the models, statistical models that tell what the density function is. For instance, if they wanted to have a circle etched, they would be able to find the probability density function related to the radius of that circle. And they'll have a mean value of probably the value they want, and then there'll be a variation. So you can figure out everything that's going to happen with these. Basically, if you're doing line widths, you want to make sure there's very little chance a line width can bleed into an actual surface, you might say structure of a transistor or something. So you can statistically design these things for the minimal chance of a problem, but the maximum packing density. So all this stuff is based on, a lot of times, 2-dimensional actual density functions. So what that means is if you have f of x, y, this right here is going to be a 2-dimensional density function, or probability density function. It's just like density function that had only 1 variable, exactly like it. So some of the things that I have to say, I think everybody knows is, if you integrate the density function over the range of all possible values, you end up with 1. That's obvious. The next thing that's obvious is f of xy has to be 0 or strictly positive. It can't be negative. You all follow me on this? These are just things that are, in my opinion, obvious. They're basically just carryovers from the density function of 1 variable. With me on this, class? The other thing about this is these density functions would give rise to a cumulative distribution function that has 2 dimensions. Now, the only thing I'm going to tell you is this. When you look at this cumulative distribution function, you're saying that the probability that some value of x and some value of y is going to occur, or that value puts the limit that somewhere between minus infinity and those values of x, y, it occurred. You all with me? And what is that going to be? Well, it'll be f of x comma y dx dy. And here, the lower limit has to be infinity minus infinity, even if it isn't. They put that there, so as you come up the line, say it's 0, it starts at 0, then you put a 0 there, the lower limit, to some value of x and some value of y. Technically, I should prime those, but I don't worry about that. And that's the cumulative distribution function. And that, by the way, in the limit, as x comma y go to infinity, f of x, y has to go to 1. In other words, the event has to occur over the entire event space. I think you understand what I'm saying, right? All right, now one other thing that happens is if you want just f of x or just f of y, and you have f of xy, you can get it. F of, say, y of y is simply going to be the integral of f of xy, and in this case, it would be dx going from minus infinity to infinity. Basically, you're integrating out the other variable. You follow me on that, class? That will give you just f of y. And likewise, if you want just f of x, you would integrate f of xy, and then you would have dy. Do you all follow me on this? Now, there's a couple things. I'm not sure if I did this. Did you guys see slides from chapter 3 from Tom Denny, Dr. Denny?
I don't think so.
Tell you what, I'm going to put these up here, and I think this is very logical. There's nothing here that's new and takes a lot of rational thought. Go through them and then do the problems, because I think, honestly, seeing how this is applied to problems is the key to understanding the theory. So I wish I had my glasses. And for what life for me, I thought I had them. So let me just see if I can get this. By the way, I appreciate you coming today. I know we're missing 2, 4. We're missing Jagger, your papers. We're missing 3 people. So 2, 4, 6, 8, 3 or 2. We're missing those. So I'll show you this. I was thinking about the best way to do this. I hate PowerPoints, but in this case, because this stuff is, in my opinion, very obvious, I don't think I'll have a problem. Don't turn the lights down yet. Let's see if I can get this to work. Can you all see that? Okay. Now we're talking about can you go in the back there and just punch the center button right there in the light switch? And then try the upper left. No, hit that center button. Try the upper right. No, okay. Lower left. Yeah, we'll work with that. Can everybody see this? I'll post these things and send me an email to remind me. This is actually very useful here, because he does a great summary. So anyway, that's what I just said about the cumulative distribution function. The probability of x being less than or equal to some value, and y being less than or equal to some values, f of x, y, for the joint probability. The properties I mentioned, basically, you know that this thing has to be between 0 and 1. And then you also know that basically, if you look at the limit when either x or y is minus infinity, the value of that has to be 0. Just think of f of x, if x, or f capital F of x, if x is minus infinity, it is 0. Correct, class? Let's see here. That's just saying that the probability the event occurred has to be 1 if it's a realizable function. It's non-decreasing, it has to keep going up or stay the same. And if you notice that, what he's saying is, if you take x at the extreme possible value, which means that f of x is 1, or the capital F of x is 1, you get f of y. And likewise, if you take y to infinity in the joint commutative distribution function, you get capital F of x. And this is just saying basically how you end up defining what f of y is or f of x based on the joint density functions. All right, now this is something I didn't put up there, but hopefully you recognize this. If we have a cumulative probability density function, you want the probability density function of f of x, y. Take a derivative with respect to x and y. Does this make sense to everybody? It seems as clear to me as the other one for just one dimension. There's nothing new in terms of theory. This is just saying that f of x, y integrating gives you the probability density, or the cumulative distribution between x and delta x and y and delta y. Finally, that's what I put on f of x, y has to be greater than or equal to 0. And that, what we already talked about. And that's how you get the cumulative distribution function. Now, the term he uses is a joint density function of f of x, y. You can use that term, but it's really a density function of 2 variables. Is all it is. Okay, here's a pretty cool example. It's a simple one. So they're going to say this joint density function, f of x, y, is defined over a given x range and y range. The minute you know that, and he says it's constant, I think, if it is constant, the only thing you have to do, if you want the value of f of x, y, if you know the actual dimensions where the variance is in y and in x, you take those 2 limits. It's like looking at width times height. If you take a look at that, that's the area. Whatever that area is, basically the height of that, that's basically going to be the height. It's 1 over the area, and that's what he's showing you right there. I didn't say that exactly the way I wanted, but help me understand this. It's basically saying the height under, or if you integrate f of x, y, if it's constant, the height of that, if f of x, y is constant, the height of that times the actual area has to be 1. So we can get the height or the magnitude of f of x, y that way. And the expected value of a function of x and y is just multiplying that function g of x, y times f of x, y, and integrating over the possible range. By the way, that should make perfect sense in my opinion. Just as before with 1 dimension, if we want the expected value of any function, take that function and multiply it by the density function, integrate it. Does this make sense? This is just an extension to 2 dimensions, right? Can everybody see this right here? It's not meant to be tricky. I want to get the problems. All right, the expected value of x, y. Now this is going to be real important in a little bit, because we're going to get something called a correlation coefficient. Well, just like any other expected value, you take whatever's inside there and you multiply the density function by that and then integrate it over the possible range. What you're not familiar with is something called correlation yet. Have you had the term correlation in mathematics yet? It is a relationship of how similar one thing is to another. That's all it is. It's a measure of the similarity. And when things are correlated, it means they're related or similar, or there is some way that those two vary in a predictable manner. Just try to understand it. We'll get to the exact definition in a sense. And by the way, you know what convolution is, right? You convolve things. Correlation is almost identical, but instead of, for convolution, I'll talk slowly here. Do you remember if you convolve two signals, say h of t and x of t, it would, if it's continuous time, it would be an integral over the range from minus infinity to infinity of, and then you would put x of tau times h of t minus tau d tau. Do you all remember that? Well, in correlation, it would be the same integral from minus infinity to infinity of x of tau, but then it would be h of t plus tau, not minus. That's the only difference. And you'll find that when you do correlation, in fact, what you get is going to be a signature, if you have a functional form of it, that is just flipped. Correlation is the flipped convolution of the two signals. And I'll have to show you that because it's not exactly clear. There's the example. We're going to get, what I'm going to say is that these examples I'm going to skim through and get to the actual problems where I'll ask you questions and you tell me how to do them. Because that's where it can get tough, you know. This is just a trivial example. And we'll get to the probability dimensions are over a certain limited range. So we'll get through this. We'll get to that. An expected value of xy, which would be the area. Now we'll get to the joint density functions, but one thing, you see this density function right here? The joint density function. We know one thing for sure. If I integrate that over the range of possible values, I have to get 1. So if there's an unknown constant, in this case a, can you all see this? When you do the integration of this thing over for the range given, and it's all for positive values of x and y, it has to be 1. So if you look at this, how do you find the value? Well, you set 1 equal to the integral of a e to the minus 2x plus 3y dx dy. And lo and behold, you basically have a problem where you calculate a by doing the integration. Take the inverse of that. You all with me on this class? Now, I gotta tell you one other thing about this. That's how you calculate the joint density functions, probability of x or y being over a given range, but let me get to this. Now I'm going to do some problems on the board that I think are telling. Because I'm going through this quick, I think it's very easy to understand. That's the only reason I'm flying through this. So. Can you hit the lights? I'm going to get this done yet. So can you read me problem 3 in the back of chapter 3, 3-1.1. I might do some of these out of Chan too, but I think right now I'll just stick to what I think is here. What does it say?
2 random variables have a joint probability distribution function defined by f of xy equals 0 when x is less than 0 and y is less than 0.
Go ahead.
Equals xy when 0 or 0
Is
less
this
than
the probability density function or joint density?
joint probability.
Joint density function.
Yeah.
All right, hold it, that's capital F. So capital F of x, y equals x, y, and this is for x, y greater than 0, right?
Yeah, greater than 0,
Less than 1. Whenever I do this class, whenever I have like 0, greater than x comma y, less than 1 means both variables are over that range.
Well, they have this one, so they have the y after the 1, so that y is greater than the 1. Or I guess, no, it's common, yeah.
It's gonna say this is what it is here, and then it should say 1 for x comma y greater than 1. That's what it should say. It's just saying the range, where the actual value varies is between 0 and 1 for both x and y. After, for x and y greater than 1, it's 1. Are you with me? Okay, go ahead.
And then when it's 1, it's x is greater than 1y is greater than 1.
Yeah, it's basically, anytime x and y are both greater than 1, it's 1, that's it. That's the only thing he's saying. Go ahead. Or the event happened.
It says sketch this function.
Okay. Just for brevity, I'm not gonna try to sketch a two-dimensional function in my artworks, usually questionable at best. Go ahead.
Find the joint probability density function.
Pay attention to this one. I know I went a little quick. How would you find, what they're asking for, the joint probability density function? Yeah.
Yes.
What he's looking for is f of x comma y. How do you get it? Anybody?
It's just derivative.
Two derivatives, of one of x, one of y, of that, right? So what we say is this is going to be equal to the second derivative with respect to x, with respect to y, of that f of x, y, which is x times y. And if you look at this, what do you get? 1, and this would be for 0 greater than x comma y, less than 1, and it's 0 else. Does that make sense to everybody? What it really amounts to is it's a constant value, just like that notes I put up a second ago, the slides. This one I can sketch. If you look at this, if this is x and this is y, and here's 1, and here's 1, the only thing this is basically going to be height of 1 for f of x comma y greater than, between 0 and 1. Follow me? It's constant. Does everybody see this? That's it. Now go ahead.
Find the joint probability of the event x is less than or equal to 3/4, and y is greater than 1/4.
Okay. Now they say the probability of x, what was the range?
X is less than or equal to 3/4.
3/4, okay. And y?
Y is greater than 1/4. But it's got these labeled as two separate events, capital X and capital Y.
Yeah, but that's just inside the probability, right? It's the probability of both occurring. Okay. Can everybody follow me on this? All right, it's real important that you get an idea. Don't let the wording throw you from this. They just want the probability of this occurring. So if you think about this, it's going to be the double integral here of the joint density function, which is 1. Those are the kind of density functions we like. And we have to integrate dx, and it's going to be from 0 to 3/4. And then dy here is from 1/4. From 1/4 to 1. Does everybody understand this? I've got the density function, it's 1, which is great. Then I have to integrate that density function over that range. So for x less than 3/4, the range would be from 0 to 3/4. Remember, it starts at 0. For y, it says y greater than 1/4. That would be from 1/4 to 1. Does everybody follow me on that? And what's that going to be? Well, frankly, this is 1. When we do an integration, we just get the variable and evaluate there. That will be 3/4 for the first part. And for the And for the second part, it's 3/4, unless I did my math wrong, and that's gonna be 9/16. Do y'all agree with that? Pardon me?
I would just say that's what's in there.
Now, does that make perfect sense? That's the reason I'm flying through this a little. This stuff seems trivial. We'll spend time on the hard stuff. What's the next part?
That was the last part.
What?
That was the last part.
That was it? Okay, next problem. Hold on, let me erase it. Does anybody have any questions? And if I'm moving too quick, just yell me out. I'll try to elaborate on anything I can to help you understand this, but this is meant to be trivial at this point. The way he's presenting, I have a feeling the way Chan presents this would not be so easy. Let's see.
Sorry, why is it, and maybe this is just me, like.
What?
Why is it 3/4 times 3/4 when you do the interval?
Well, when you go from 1/4 to 1, that range is 3.
Oh, yeah.
That's the only, there are no dumb questions. Y'all with me on this one? It's just over the range.
Thank you.
Easy to miss. 3-1.2. Go ahead.
Got two random variables, x and y, have a joint probability density function given by f of xy equals kxy.
K times x times y for 0 greater than x, comma y less than 1, is that right? Are basically the same range. X and y from 0 to 1, it's 0 else. Go ahead.
Determine the value of k. And
All right,
this is-
I'm gonna let everybody write this down. Think about it. How would you determine the value of k? We've got a joint density function. What is the key?
It's 1 over the whole range.
If you integrate that thing over the range of possible values, you have to have 1. Do you agree with that? So if you did this, remember that range, I know 1 would be equal to an integral, double integral of this, k, x, y, dx, dy. Notice the range is such a nice range, 0 to 1. Those are the things when I was a student I loved doing. And this problem becomes almost trivial, right? We integrate that and we get 1 equals, and here k you can take out in front. And then if I integrate x dx, I get x squared over 2 from 0 to 1 will be 1/2. Integrate y to y, I get y squared over 2 from 0 to 1 is 1/2. And that means I got k over 4 equal 1, or k equals 4 by looking. They're meant to be simple right now. They're meant to just make sure there's nothing you don't understand. First, does everybody agree with this? Any questions? Not meant to be hard at all. What's the next part?
Determine the joint probability distribution function, so the capital.
All right, this is the cumulative distribution function. Y'all
I'm
hear me?
wondering, why don't they call it that?
I don't
Is
know.
that just-
Whenever, if it's the joint probability density function, it's f of xy. If they say it's the density function, right?
They call it joint for both,
I mean, joint what?
joint probability density function, when it stated the problem.
But read the second part. Maybe I heard wrong.
Yeah, the second part says determine the joint probability distribution function.
All right,
And
he didn't say probability density, he said probability, right? Distribution? Is that right?
Distribution function, yeah.
That just means the integrate, it's basic capital. So if I have this, and I want f of x comma y, remember to get this, you take 2 derivatives of that, right? With respect to x and y. Well, that means to get capital F of x, y, we do 2 integrations. Y'all with me? So we can go ahead and say, since it starts right here at 0, we would integrate from 0 and to x, and, or better yet, y, and from 0 to x of that joint density function, which is 4x, right there, y, and then it's going to be dx dy. I'm gonna put a prime there. And this would be true only from 0 to 1. So this is gonna be true for 0 greater than x comma y less than 1. When you do this, you can see I got x prime, dx prime, I got x prime over x prime squared over 2. And now you can almost see what's going on here. I'm going to have 4, and then I'm going to have 1/2, and it's going to be times x squared, 1/2 here, times y squared, or simply x squared, y squared, from 0 greater than x comma y less than 1, and it equals 1 for x comma y greater than 1, and 0 below that. Do y'all follow me? How many do right here? Correct? Now, if you look at this, just look at this for a second. X squared, y squared. What is the value when x is 1, y is 1? That's exactly what it has to be, right? Before it goes out into the continuous value of 1. And it works. Is that the right answer?
Yes.
Okay. What else?
Find the joint probability of the event. X is less than 1/2 and y is greater than.
Okay, pay attention to this one. So now I want the probability of x, go ahead.
X is less than 1/2 and y is greater than 1/2.
Okay. Now, we could mess around and do it with a joint density function, but I'm going to level with you the way I do these problems. I go right for the probability density function and put the limits of that integration. In my opinion, it's easier to see it this way and you'll make less mistakes. So I'm going to say it's a double integral here. First, I take the density function, which is 4xy, then dx dy. The only thing I'm doing here is just putting in base definition of what I have to do. Now I have to put the ranges on here. For x, the integration is from 0 to 1/2. You'll notice it's x less than 1/2. So it starts at 0, goes to 1/2. Everybody with me? So it goes from 0 to 1/2. And for y, y on this one is greater than 1/2, right? So the lower limit would be 1/2, and the upper limit would be 1. Does everybody understand this? It's not meant to be tricky, but you have to be clear about it. I have it happen when they're real simple to fly through them too fast, so I want to make sure that everybody sees this. You good with this? Far back too? You good? All right, what's that going to be? Well, I'll put the 4 out here. When I integrate dx times x, I get x squared over 2 from 0 to 1/2. That would be 1/2 squared divided by 2. First, does everybody agree with that? X squared over 2, x would be 1/2 squared divided by 2, correct? And then when I integrate y dy, I get y squared over 2, but notice the limits are different. So then I put down, again, 1/2. You could write the formal thing out. And then I have y squared evaluated from 1 minus 1/2 squared. I'll put the whole thing in there. Do y'all agree with this, by the way? You can do this differently. I put down all the numbers so you can see. When you do this, let's see, what do I get? How about get rid of that? And then I have 1/2 squared, or 1/4. And then 1 minus 1/4 is 3/4, right? So it looks like it's 3/16. Is that the right answer?
Yes.
And again, it's just a simple integration, but you almost have to force yourself to be attentive with small little details because you can make stupid errors. And I'm very good at that when I'm in a hurry. Okay, what's the next one?
Find the marginal density function.
This is a good one. All right, of what?
Fx of x.
Pardon me?
Just fx of x.
All right, this is, I'm glad. So now they want just f of x of x. They're wondering about that. Remember what I told you earlier on? How to get that? Just think, I want to make sure you form the question in your mind if you don't know the answer right now. How do I get the density function of one variable if I have the joint density function of two variables? The answer is integrate out the other variable. And here's what it amounts to. This right here is going to be, in my opinion, pretty straightforward. So it's going to be equal to an integral. In this case, the range is from 0 to 1 of f of xy, right there, which is 4xy, and then you would integrate out dy. Can everybody follow me what I'm doing? You agree? What happens? Well, when you integrate out y dy, you get y squared over 2 from 0 to 1. It just means you have 4 over 2 times x for x greater than 0 less than 1, and 0 for else, anything else. So that's really equal to just 2x. Is that the right answer?
Yes.
Now this is meant to just make sure you understand the trivial things. By the way, what would fy of y be? Just the density function of y.
2y.
That's right. You can see the symmetry in this one. I don't know if they asked that, but do they? Is that it for that problem, or they got one more?
That's it.
Okay, let's go to the next one. I'm actually on schedule.
For the random variables of problem 3-1.1, find the mean of x and y.
So 3 dash.
This is 3-1.3,
All right.
but it's when we use the function from 3-1.1.
3 dash 1.3, and we need the density function for the first one. Remind me what the first one says.
It was f of xy equals xy from 0 to 1.
Capital F. Thanks.
Yes.
All right, that means this density function is 1 from 0 greater than xy less than 1 for both of those, and 0 else, right? And what do they want now?
The mean value of x and y, or
Okay.
expected value.
So what they want, the expected value of quantity x, y for that density function. This is a tricky one, guys. Promise you. Do y'all hear me? How do you get it? Well, you're obviously going to take the integral of the density function, which is 1. Right? Over that rate, man, it's the probability density function. And then we're going to multiply that by x times y, integrated dx dy, but the range is so nice. It's 0 to 1, 0 to 1. This one, you all agree with that? And again, just take the probability density function, joint probability density function, xy, multiply dx dy, I'm sorry, it's 1 times x times y. You do the integration. And for this one, you're going to get x squared over 2, y squared over 2. And unless I've done something terribly wrong, it looks like it's 1/4 by inspection. Is that right? Y'all follow me on this one? It's just meant to be almost trivial. You're almost looking for something a little more complicated. But it's that easy for this one. Now, where it gets hard, I mean, suppose you get something where you got this is going to be like e to the minus x, all right, over that range, something like that. And then you multiply by x, then it becomes an integration by parts, and it can get progressively more difficult to do that integration. But the theory is basic. Just remember that. What's next?
The same thing, but using f of xy equals kxy, the one we did before, so 4x.
Okay, so for now they say, what if we use the second density function that we actually figured out, which is 4xy for x comma y greater than 0, less than 1, and 0 else. If we have that density function, and we want the expected value, again, same exact type of integration right here. Double integral over the range from 0 to 1. It doesn't get easier than this in terms of the ranges. And then I get xy times this. So really I'm going to get 4x squared y squared dx dy. I'll let you copy that down. But the only thing I've done is that's the density function, 4xy, and I have to multiply it by xy, right? So I'm going to get 4x squared times y squared then. I want to make sure everybody sees that before I go on. Are we good? And in the back. You good with this? All right. What's that going to be? Well, take the 4 out in front. I integrate x squared dx. I get 1/3 x cubed. Y'all agree with that? Then I integrate y squared dy. I get 1/3 y cubed, or just square that. And that means 4/9 should be the expected value. Is that right?
That's right.
All right. What's the next part?
That's the last one,
For
or 1.3.
all right, then there's one in 3-1.4. Then he didn't actually, he didn't assign that one, but it's basically dice. And it's going to say, I have an event called X, which is the outcome of a roll of the first dice, or first die. And then Y is going to be the outcome of the second die. Y'all follow me? So we got 2 dice, we're rolling. The possible values are from what? 1, 1 to 6, 6. Follow me? Each one of those, and like for X, it has a probability from 1 to 6, or 1/6 the probability of any of those values. Y, it would have the probability of 1/6, so the joint density function would be 1/36. And you should say that. I'm not going to do this one in its entirety, but get that in your mind, right? Joint density is going to be 1/36, right? Constant for any values within the range x from 0 to 1, y from 0 to 1. Can anybody imagine it? It's discrete though. It's not continuous. Got that? Then he asks for what?
Found the joint probability of the event.
1/36 it's given. Is that right? Yeah. He's nodding his head. Yeah, but this is discrete, not continuous. That's the difference. What's the next part?
Found the expected value of xy.
Okay. So I'm going to make this claim. The event x and the event y are independent. One does not depend on the other. Can we agree to that without a lot of mathematical proof? So if I find the expected value of either one of those, and I square it, wouldn't that be the expected value of both? Because they are independent? So what is the expected value of rolling die? Well, it's 1/6 times 1 plus 1/6 times 2 plus 1/6 plus 3. Follow me? So I got 1 plus 2, 3, basically 3 plus 3, 6. 6 plus 4, 10, right? 10 plus 5, 15. And 15 plus 6 is 21, right? I'm just showing. Do y'all agree with the theory? Then divide that by 6, right? 21 by 6. Wouldn't that be the expected value of one die? 21 by 6 squared. Let's see if we're right. Isn't that what it asks for, the expected value? Yes. All right, so what's 21? I don't know this. I should. Squared. Let's see what I did it like. Anybody? So 3 times 7, 9 times 49 over 36. I can't do that quickly. Anybody? Everybody.
12.25.
Is that the answer? All right. You got the idea on that one, class? How many do? Now, is there another part to that one?
It says find the expected value of x over y.
And again, this is one of those things, x over y. So you got one outcome over the other, right? And what does that entail? All right, x times y we just did, right? X and y are independent, so it's this. The expected value, if they're independent, and first we have to agree they are independent. Do you agree with that? So that's going to be the expected value of x over y. If these are independent events, it's expected value of x, which is 21 over 6, right? Times the expected value of 1 over x, right? I want you to think about this. Is a cool one. Expected value of x, we got 21 over 6, correct? What's the expected value of 1 over y, or something like that, right? It won't matter, but you could do it that way. Follow me on this one? The expected value of x over y is expected value of x times expected value of 1 over y, if they're independent. First, we have to agree on that. Do you agree on that? We've got the expected value of x is 21 over 6, right? How do you get the expected value of y? Just think about it. It's going to be 1/6, right? Because that's the probability of any value of 1 over y occurring. And the first one, if it's 1, it's 1. If it's 2, it's 1/2. You all follow the logic on this one. Remember, they're all got a probability. This is for 1 over y of 1/6. Plus, this one I can't do in my head either. Plus 1/4, plus 1/5, plus 1/6. And what's that going to be? Let's see. Oh, I hate doing these. Can somebody do this for me? 1/6 times 1 plus 1/2 is going to be 3/2 plus 1/3, 9. Can you just tell me that? Anybody? Well, look, you know how to do that, right? You get that value multiplied by 21 over 6 and you get the right answer. Because I don't know what it is. But you follow the logic, that's the key thing. There may be a trick I don't see. I'm just gonna roll with this one. He has something like that, right? Is there another part to that one?
That's it.
Thank God. Now, we move on to the next stuff that I want to cover, because I'm doing this quickly, but I'm trying to really make some points here. This is not hard right here, not at this point. It will get difficult. And if you can do the lights, please. One more time. This ain't so bad doing, doing the PowerPoint and then applying. What comes on? Okay. Can you guys see? So, conditional probability. Now, y'all remember when we did Venn diagrams and I had an overlap of the circles A and B? And you said, I said it was always the probability. It's basically proportional to the joint area where A and B intersect, divided by just the area of B. That's the basic thought that should be in your mind when you're doing this. If you look at this, what is the probability density? He gives you sort of an actual, of the actual voltage given, the measured value of the voltage is 1.2. These are, do you remember when we did that thing where we had a sender and a receiver of a 0 and a 1, right? And what we wanted was probability of 1 occurred if a 0 was sent, probability was 0 occurred, 1 is sent, stuff like this. This is that kind of a thought, but this is a neat way to do it. So if we have, we're doing this now with a joint density function. You haven't seen this part before, so pay attention. It makes it easier, a lot easier. Basically, the probability of x less than a certain value given y less than a certain value. Now notice the last part right here. F of xy over f of y. Do you remember how you get f of y, just f of y from f of xy? You basically do what? You take the x in f of this class? Now, how does that apply? Don't worry about this part, let me get to the actual. But I believe it says it all. This is an easy way. So if you look at this, f of x, given y has a certain value, is really f of x comma y over f of y, evaluated at that certain value. That's nice, because you can get f of y easily if you have f of x, y. You're following me on this class? Just by integrating out x. And then it goes through base theorem. If this is true, then f of y, given x has a certain value, would be f of xy over capital F of x. You follow me? How many understand this? Basically, it's the inverse there. So Bayes' theorem, because f of xy is common with both, you can get the conditional probability or joint probability. This is, I'm going to tell you what this is. It's basically Bayes' theorem applied here. Is going to be this. And you'll notice that if you have f of xy given f of y given x, you're going to simply going to use the f of x in the denominator and vice versa over here. I'm trying to get this where I can show you the applied. So conditional probability. Here I have f of x comma y is k e to the, or k times x plus y. I want to tell you right now, if x and y are independent, then you should be able to factor the density function f of x comma y, the joint density function, into just the function of x and just the function of y. Do y'all hear me on this? It means like if you had something f of x y is 4x times y, you can get 4 times x is just the function of x times just the function of y. But whenever you have that plus, kx plus y, you cannot factor that into two functions that are just one as a function of x and just one as a function of y. By that multiplying, I mean, this is additive. Can you all see that? It will not be something that the x is independent of y. Now let me get down to this. The value for k, how would you get? Simply integrate that over the range from 0 to 1 in both x and y. Do you agree with this? Set it equal to 1, find k. Don't worry about it right now. He shows you how to do it, and therefore k is 1. Just trust me on that one, it works. Next, he says the probability that x is greater than a half given y is 1/4. Now go back over here where you see, hold on. Well, they give you the value of y. So I could take the value of f of xy, integrate it from 1/2 to 1, and then divide that by f of y equal 1/2. Now, he'll show you this. You're going to have to do some problems to appreciate this. So here's f of y by doing the integration. With me, people? Hang in there the last few minutes. And see that one? That's what I was talking about. This is so much easier than a lot of the other conditional probability ways to do it. So you got f of xy over that, and you can see for a given value of y, if it's specified, you can get this very easily. Do y'all follow me in this class? Mathematically, it's trivial. Now, all right, he gives you a homework. I'm going to give you that homework. Just put it down. 3, I don't like to give you a lot of homework when you get a big break. But I want to ask you to do 3-2.2. And let me finish this. Give me another minute. I'll be a very happy guy. Now, I was mentioning this, just listen. If you have two random variables, x and y, and you have a joint probability density function, f of xy, what I was getting at, the only time they're statistically independent, one does not depend on the other's outcome, is if you can factor them like this into two separate functions. else, it means that they are. And we'll get to that more. And by the way, if f of x and y are independent, f of x given y, if you think about what it means to be independent, it's just f of x. If x doesn't depend on y, then it's just the density function of x. It's all, it doesn't matter what y is. And let's see, the expected value, therefore, if they are uncorrelated, is just the expected value of x times expected value of y. So you got two random variables. The last thing, here's the joke, are they independent? I think I gave that away. Are they? Why not? You're right.
So they're inseparable?
You can't create just the function of x times just the function of y. You all follow me? They're additive, but that doesn't mean they're actually independent. They're not. No. Thank you. Are they? Take a look. If f of x is 4x times y class, yes, they are, sure. Because you can, x is just a function of x, y is just a function of y. Sure. And so, back here, if the expected value of x, y is just the expected value of x times the expected value of y, they are uncorrelated. Now, it's almost by definition, if they're statistically independent, they are uncorrelated. But the formal definition of uncorrelated is the expected value of the product of the two variables. It's just the expected value of one times the expected value of the other variable. That's the definition, but I don't really care about this. So I'm gonna put these notes up there and ask you to do problem 3-2.2. I may ask you to take a look at something in Stanley Chinan's book. I haven't really looked at it. I have my glasses around here. Please let me have it. You can't see without your glasses.